Colombia. So my poster is about NOVA constraint on CP violation non-standard interactions. So NOVA experiment is a long baseline experiment and has two detectors, the near detector and fat detector. So the main study is neutrino oscillation, the CP violation phase, the neutrino mass ordering, and physics beyond the standard model. So in physics beyond the standard model, we have a steady neutrino study, decay neutrino, also the non-standard interactions. So the analysis of the poster, we show the phenomenology of non-standard interaction, how affect the probability oscillations. So the non-standard interaction, they are in general complex. They are complex. So they have a new delta CP violation phase for each NSAI parameters. So there is a probability oscillation for different value for one of the new delta CP phase. Also, I'm showing the reconstruction, the far detector energy spectra for NOVA with NSAI. And also, we are showing the low region for these new parameters, like we are showing the second picture. So also, we are showing how is the effect of NSAI on the standard oscillation parameters. I mean, how they affect the measure of that. So that's it. I hope that you come and see my poster and ask if you want. That's it.
Thank you. Next one. So please do the following. Put this, just the camera can follow you, and then you take off when you finish. So it's Eliana.
Okay, good morning. I am Eliana Depaoli. I'm a PhD student at Buenos Aires University. And I'm going to present in the poster a new result that CONI collaboration working with Atucha 2 experiment had achieved. Nuclear reactors are powerful sources of neutrinos and gamma. So this is why they represent a good opportunity to study standard model interactions as sevens, coherent elastic, neutrino, nuclear scattering, and beyond standard model interactions. And in this context, we have tested our experimental limits to the fractionary charge of the milli-charge particle, which you already know. These two experiments uses a Skipper CCD as a matrix detector. These are imaging sensors that can have the ability, the capability of counting electrons one by one, because one can read repeatedly and in a non-destructive way the charge created by ionization and held in their pixels. And this is why they achieve a very low energy threshold in the spectra. And CONI especially has achieved the lowest threshold with these sensors, and taking advantage of this capability, and also that both experiments have achieved a very flat spectra in reactor of conditions, and that interaction of milli-charge with a matrix, as you can see in this plot, where the cross-section of the milli-charge with silicon is plotted. You can see that the cross-section has an increase in in its value at very low energy, near 15 eV. This is due to the interaction of the milli-charged particle with the plasmon bulk in the silicon. And so taking advantages of all of this, we were able to calculate our exclusion limit, experimental exclusion limit, and we were able to improve the best limit previously established by the Texono experiment. So I'm going to present this result in the poster. Thank you.
Thanks. So next one, Guilherme.
So I'm Guilherme Nogueira, and I recently started my PhD in neutrino physics, but I will present the work of my master's degree, which is higher order QSD in Higgs into gluon-gluon, under supervision of Diogo Boito. Basically, what we made here was to make a prediction of the first to know coefficient of the Higgs decay in two gluons in perturbation theory, using rational approximants, known as Padé approximants. We use the half-top limit. This is a good approximation for this case, where basically the quark top mass is considered as infinity, and in this limit, the Higgs couples effectively with gluons. We have also explored how our final estimates impact the Higgs decay into gluons. Basically, a physical quantity should be almost invariant with respect to the renormalization parameter, renormalization scale parameter. And in fact, our final result in the black line is the central value of our estimates, and the yellow range is the uncertainty, Gaussian uncertainty. And it is almost flat. And we have also our numerical prediction in pink and its uncertainty. And that's it. If you have any question, go to my poster and we can exchange ideas. Thank you.
Thank you. So now is Juan Román.
Hello. I am a student of Master in Universidad Nacional Autónoma de México. This is the model. I introduce a SU2 local symmetry in the Vision standard model. This symmetry is considered spontaneous breaking by the doublet phi. The Goldstone bosons give the mass to gauge boson, and the last boson appear like a scalar boson eta. Eta mixes by Higgs boson in the physical basis. This model have the rotational symmetry SO4. This symmetry breaks to SO3, and this group is isomorph to SU2. This symmetry is called custodial symmetry, and the custodial symmetry stabilizes the gauge bosons, and their masses are degenerate. Don't exist the interaction between the fermions of the standard model and the gauge boson without violating the custodial symmetry. This is the results of the model. In the first graphic, for the two observables, the relic density and the cross section. The relic density, the model can predict the relic density by Planck measurement. The second is the cross section. All the favorite parameter space are above to the neutrinos floor and have possibility of direct detection. And the last graphic is for a reduction of parameter space of a couple constant and the mass of eta. Okay.
Thank you. So now we move to Manuel.
Okay, hello. I'm a PhD student in the Universidad of Buenos Aires. This is my master's thesis I presented a couple months ago, which I did in the University of Buenos Aires and in collaboration with the Brookhaven National Laboratory in the US. So basically, when we add the Higgs potential to the Lagrangian, we get these terms for the Higgs field, a kinematic term and two interactive terms. And so we're studying the tri-Higgs coupling, which is this term with the Higgs field at the third power. So the thing is that this lambda parameter is not measured with precision yet. It's one of the few, if not the only parameter in the standard model that has not been measured with precision. And it can be a gateway to new physics, to beyond the standard model physics, because it changes the shape of the potential, of the Higgs potential, right? So what I did is study this process, this vector boson scattering process, where we have the tri-Higgs coupling in the middle, and because of its topology, it can lead us to differentiate this signal from the standard model background, which is pretty big in comparison with the cross-section of this event and any event with this coupling. So through simulations, Monte Carlo simulations in the Atlas detector in the LHC, I did a study of the kinematic properties of this process, some cuts in its kinematic variables, and performed a likelihood fit, trying to discriminate the signal from the background. So far, I got a significance of 0.4, which is promising to further studies with higher, with more statistics, because it was a little sample. So thank you, that's it, and you can ask me more in my poster.
Thank you. Now we move to Mateus.
Hi, everyone. My name is Mateus Paixão. I'm a postdoc at Federal University of Rio Grande do Norte, and I will present to you a work that I developed during my PhD time in CBPF. The title of my poster is Unruh effect under the quantum trajectories formalism. The Unruh effect is a very, very important effect in quantum field theory, because it shows to us that the notion of vacuum state is actually observer dependent. So if I have two observers, one inertial observer in cosmic space and a second one uniformly accelerated in relation to my first, the vacuum of the inertial observer will be the same vacuum of the accelerated observer. So the notion of particles itself will depend on my reference frame. Actually, while the inertial observer will see 0 particles in the vacuum, the same state corresponds to a Bose-Einstein distribution for my uniformly accelerated observer, with the temperature being proportional to the acceleration. So this is a very important effect if we want to study, for example, black hole radiation. And the idea to use the quantum trajectories approach, the quantum trajectories is basically a different interpretation of, alternative interpretation of quantum mechanics that works a lot with this notion of trajectories of quantum particles. And the idea is because the notion of entanglement is very intuitive in this interpretation. So If anyone here wants to discuss about these topics and who affect the quantum trajectories formalism and possible applications to dark matter, please go to my poster and I will be welcoming you and I will be very pleased to talk to you. So thank you so much.
Thank you. And the last one for today, Valéria Vale. Valéria, Valéria is your name? Valéria.
Good morning. My name is Valéria. I'm a master student from the Instituto Tecnológico de Aeronáutica. And well, when a relativistic particle pass through liquid argon in large EPCs, two processes are likely to happen, such as ionization and excitation of argon atoms. Well, when it happens, these processes happens, will be produced UV photons and free charges, which we can relate to the light yield and the charge yield. The Larkwell model is a phenomenological model that provides an anti-correlation between light yield and charge yield, both depending on the electric field and the deposit energy. My poster will show you the prospects of this model, the new hypothesis, the implementation of the global fit to this model, and the results of the inclusion of new data of light yield and charge yield. Well, if you want to ask me, if you want to discuss more about this topic, I'm the owner of the Lavendish poster, and feel free to ask me anything about it. I will do my best to answer you. Thank you.
Thank you. Okay, just to check that we end. Okay, that's good. So this is the 7th poster for today. So I ask the presenters to be near the poster by the coffee break, and the others can go and make questions and discuss about these interesting topics. Before going to lunch, let me explain one thing. For the experimental part, most of the experiments will require to do some kind of data analysis. So the soft that we will use is the soft that we are common to use in particle physics, and it's listed here. I guess that a lot of you are familiar with that, but if not, and if you want to start to install things in your computer, you can do it, but especially from the experiment 2 that relies on Giant 4 simulation. Giant 4 is gigant and is very difficult to install and takes time. They prepare a virtual machine that will be available by Friday, maybe before. No problem, because it's very easy to install that. And this virtual machine also will have all of this soft that you need for that experiment. So I wanted to let you know that this is what we will require, because maybe you already have or you like to install. So feel free to do whatever you want, but don't spend time if you don't know how to do and if you have difficulties, because in the time machine, in the virtual machine, you will have that, okay? We will put this virtual machine in the site of the school, but also we will have some memory sticks with that, so you can copy and we will let you know. Don't be anxious, because we are working on that and we will divide this. Just again, because we have many questions, we have a pool of 9 experiments. Most of you will be able to do 5 of those, okay? And this is what we will present on Friday, and this is what you will choose by filling a Google form. And on Monday morning, you will know the schedule of the whole week. So we have some students that will choose to do at the full school that did not show up. So some of the ones that will choose to do only the talks of the school, let's say like that, will be promoted, and we will let you know this by Friday, because you will be able to choose the order of these 9 experiments using the Google form, okay? So everything will be ready for Friday, and I will announce here, but also we will send an email to you so you will know. Don't worry about that, okay? Any question? Good. So then, don't leave the room before signing the presence list that is here, and don't remove this present list from this table because we lost the one from the afternoon. If you have the one from the afternoon from yesterday by chance with your staff, please give us back. Otherwise, we will print another one. And then if you left this here, I can change by the list, okay, for the list. Okay, have a nice lunch, and we recombine here at 2 o'clock. Be on time. And remember that today is holiday, so we suggest you to go to the same place that yesterday that we know that is open, okay? Thank you.